When an MCP server reaches production, it works is no longer enough. You need to know who used which tools, what failed, how long it took, and whether behavior stayed safe. That visibility is the role of observability. You've already built the foundation: how MCP servers work, how to secure them, and how to design predictable tool interfaces. Now we shift from building correctly to running reliably. We'll begin with observability, then connect it to deployment, scaling, governance, incident response, and production readiness. An MCP server sits between an AI client and systems that may contain sensitive data. That makes visibility essential. Because the client may choose tools dynamically, traffic patterns can be less predictable than a typical API. Observability shows what was requested, which tool ran, whether policy allowed it, and what happened next. Logs, metrics, traces, alerts, and audit records turn those events into operational evidence. With them, teams can debug failures, manage latency and capacity, investigate security questions, and prove compliance. Without them, an MCP server is difficult to trust in production. A useful mental model is to treat observability signals as different lenses. Logs provide the narrative for a request, session, tenant, or tool call. Metrics compress behavior into trends, such as rate, latency, errors, saturation, and overall health. Traces connect the path across the MCP server, authorization checks, downstream APIs, databases, and external services. Security and audit events capture policy meaning: allowed, denied, suspicious, or compliance-relevant activity. Strong production visibility comes from combining these signals, so an incident can be detected, explained, localized, and reviewed. Structured logging turns operational events into evidence. With JSON, each record uses predictable field names and types instead of one-off messages like tool failed. Capture identifiers such as request ID, session ID, tenant ID, client ID, and tool name so one user action can be followed across services. Record timing and result status consistently as well: success, validation failure, authorization denial, timeout, downstream failure, or rate limit. At that point, logs become more than developer notes. They become queryable data for incident response, audit trails, user session analysis, and performance monitoring. Think of each MCP request log as a reconstruction packet. Correlation fields stitch events together across services: request, trace, span, session, and sometimes conversation identifiers. Identity fields answer who acted, for which tenant, through which client, and whether delegation was involved. Tool fields explain what ran, including tool version, schema version, latency, status, and output size class. Risk fields capture why the request mattered: authorization outcome, error category, policy applied, sensitivity, and risk level. Together, these fields turn scattered events into an auditable story. Observability is essential, but logs can also become a leakage channel. Treat every tool input and output as potentially sensitive until proven otherwise. Never record raw passwords, tokens, credentials, private files, or regulated personal data. Instead, log safer signals: whether a field was present, the schema version, payload size, result count, or a short redacted summary. Apply redaction, hashing, tokenization, or classification before data leaves the server. Make the policy tenant aware, consent aware, and retention aware, so debugging does not cross privacy, audit, or compliance boundaries. Metrics turn individual MCP server events into operational signals. Start with demand: how many requests arrive, which tools are invoked, and which tenants or clients drive usage. Then separate failures by cause, because validation errors, authorization denials, downstream failures, timeouts, rate limits, and internal errors require different responses. For latency, percentiles matter more than averages. A healthy P50 can hide a painful P99. Include trust and resilience indicators too, such as auth failures, rate limit activity, and dependency health. Together, these become service-level indicators that show whether the server is fast, reliable, secure, and scaling correctly. Labels turn a metric from a single number into something you can investigate. Latency is useful, but latency by tool name, result status, error category, tenant tier, client ID, and environment can answer real operational questions. Which tools are slow? Which clients are failing? Which tenants are affected? The risk is cardinality. Every unique label value creates another time series. Raw user IDs, request IDs, session IDs, or free-form inputs can quickly drive up storage and query cost. Use metrics for aggregate patterns. Use logs and traces when you need the exact request, user, or payload behind an incident. Good labels summarize. Risky labels enumerate everything. Slows turn telemetry into promises the team can manage. For MCP, define them at two levels: the server as a whole and the tools that matter most to users. Good indicators are concrete, such as P95 invocation latency, successful call rate, and authorization decision time. Be careful with the error definition. A refused request may be correct if policy, validation, or permissions require it. Separate those expected refusals from true user-visible failures. Then use the remaining error budget as a decision tool. Move faster when the budget is healthy, and slow down to invest when it burns too quickly. Dashboards should match the questions each team is trying to answer. Operators need to know whether the service is healthy right now: uptime, traffic, latency, errors, saturation, and dependencies. Developers need clues that explain why behavior changed: tool failures, schema validation problems, retries, slow backend calls, and exception patterns. Security teams watch for risk: authorization failures, unusual tool usage, tenant boundary violations, suspicious clients, and high-risk invocations. The shared requirement is drill down. A top-level symptom should quickly lead to the logs and traces needed for investigation. Distributed tracing gives every MCP tool call a continuous story. Start the trace when the client makes the request, then propagate that context through the server handler, authorization, policy evaluation, the tool adapter, and each downstream dependency. Each important step becomes a span, so latency and failures are tied to the operation that caused them. Add attributes that help investigation, such as tool name, tenant classification, result status, error category, and dependency name. With this in place, slow tools, retry storms, authorization bottlenecks, and broken backends stop being mysteries. During an incident, start with metrics. They tell you that something is wrong, whether it is error rate, latency, denials, or saturation. Next, move into traces to see where the failing request slows down or breaks, especially across service and dependency boundaries. Then inspect structured logs for the exact request ID, user, tenant, client, and error category. The critical glue is the correlation ID. When the same identifier appears in metrics, exemplars, traces, and logs, the path from alert to root cause becomes shorter, and resolution becomes evidence-based instead of guesswork. Good observability should reduce risk, not create new ones. Start with data hygiene. Do not log secrets, raw prompts, tool outputs, tenant data, or sensitive payloads unless redaction and policy review are in place. Keep metric cardinality under control, because labels like request IDs, raw user IDs, and free-form inputs can turn one metric into millions of time series. Alerts need discipline as well. Page people for user impact, SLO burn, security anomalies, and critical dependency failures, not every warning. Finally, govern observability data with retention, access controls, sampling, and regular review. The main takeaway is simple. Production confidence comes from observability. Structured logs show what happened and who was involved. Metrics and SLIs reveal health, latency, failures, and trends. Distributed traces connect the full request path across clients, services, and dependencies. With that foundation in place, you are ready to move into deployment, scaling, versioning, governance, and incident response.